Hello, everybody. Thank you for joining today's webinar, Incrementally Porting Applications to GPUs using CUDA.jl version 5.4. My name is Sanjeev Dasgupta, and I'm the Marketing Manager at JuliaHub. Today's webinar would be led by Tim Besard. He's a software engineer at JuliaHub, working on compiler technology and responsible for CUDA GPU backend of the Julia programming language. With this, I'll hand over to Tim. Over to you, Tim.
Thank you, Sanjeev. Can you see my screen?
Yes.
Great. So yeah, I'm Tim. I'm a software engineer at JuliaHub. I'm mainly working on CUDA.jl, but also on the other GPU backends that Julia has. And today I'm going to focus on one of the features that CUDA.jl has recently gained, which is much improved support for unified memory. And unified memory can be used to simplify how you port CPU applications to the GPU in Julia using CUDA.jl. So first, I'll describe what the typical issues are with porting applications. I'll explain how unified memory can help and what a typical workflow for that is. And at the end of my presentation, I'll also highlight a couple of other noteworthy changes that are part of CUDA.jl 5.4. So first of all, porting CPU applications to the GPU in Julia is generally relatively easy as long as your application has been written with generic programming in mind. That means using typical array expressions like you see in this example that I took from the Julia Discourse channels, where somebody implemented a small machine learning model using a proximal gradient descent training loop. And all of that has been implemented generically with generic array operations that can very easily be switched to the GPU by simply changing the type of the CPU arrays, which are allocated implicitly by a CuArray type, which is CUDA.jl's GPU array type. And by doing so, we simply get GPU execution because all of these generic array operations have been implemented in CUDA.jl or in one of the more generic array packages to run on the GPU. So this is the best case. If your code has been written like this, it's often easy to port it to the GPU. However, as I mentioned, it's the best case. You can actually run in a couple of issues. And the most typical one, the one that people most often encounter is the scalar indexing is disallowed error. And this happens when if you take a GPU array, again, a CuArray in this case, and you index it scalarly, meaning you index an individual element in that array, that actually requires a memcopy API call to fetch that single element. And as such, this is a very expensive operation. It's over 1,000 times slower than indexing a CPU array. And because that is typically used in CPU functionality that, for example, is implemented using a for loop where it iterates over every element of the array, we disallow this because it's a very common performance pitfall. And it's still possible to trigger this with functionality from the Julia standard library. For example, the unique function is something that we have not implemented in CUDA.jl. And as a result, if you call the unique function on a CuArray, it will fall back to functionality in Julia base that has been implemented with for loops performing this kind of scalar indexing. This is a very common error that users run into. Another issue you may run into is the fact that you cannot derive a CPU pointer from a GPU array because the CPU cannot access GPU memory by default. And again, you can run into this if, for example, you call into the CPU BLAS library or other CPU libraries passing along a GPU array. As a result, Julia will try to take a CPU pointer for your GPU memory, and we will block that conversion. Unified memory is a technology in the CUDA toolkit that makes it possible to automatically share GPU memory between all of the devices in your system. And this, as a result, actually makes it possible to share memory between the CPU and the GPU. Behind the scenes, it works by the driver automatically on demand paging in memory from the CPU to the GPU or vice versa, or even sending it between GPUs or between CPUs. So it's a fully automatic memory management scheme as opposed to the otherwise manual memory management scheme where you as a user are responsible for copying CPU memory to the GPU and copying it back afterwards. In CUDA.jl, we expose this unified memory very conveniently. So you have the Q function, which is an API that we have to convert all kinds of values to the GPU. Well, this Q function actually has a unified keyword argument that you can set to true. If you do so, the resulting array will have been allocated in unified memory. You can also call the CuArray constructor, setting the buffer type parameter, which is the trailing type parameter, to the unified memory type. And as a result, this array A will also be allocated in unified memory. More importantly, if you then perform array operations with these kinds of unified arrays, for example, here I'm performing a broadcast addition, or I'm calling the similar function to allocate a new array, all of these operations will copy the buffer type from the inputs, and as a result, we will get outputs in unified memory. So again, if you're working with an application, it's generally sufficient to set the initial allocation to unified memory, and the remainder of your application will, by virtue of these generic operations, take into consideration the fact that you want to use unified memory. It is, of course, possible that we've missed any of these functions or that you are performing some hard-coded allocations somewhere deep down in your application. And for that, we also support setting a preference that indicates what the default memory allocation space is. So, for example, here in my local preferences.toml, I set the default memory preference to unified. And as a result, calling the CuArray constructor without specifying anything else will now allocate in unified memory. And this again can be convenient if your application or your code or the library is not fully generic and would happen to allocate some array in device memory or in another kind of memory. Now, the benefits of unified memory, as I mentioned, is that the CPU can access GPU memory and vice versa. And in CUDA.jl, that means that these prohibited operations I've mentioned before, the scalar indexing, but also the conversion to a CPU pointer, are now allowed, which in turn means that the functionality I've shown before, the unique function, as well as calling into the CPU blast library, again, now just works automatically. And this, of course, greatly simplifies porting applications because all of the functionality that you may be triggering in a fallback code path still works. And recently, we've also been spending quite some time on making this perform well. Here, for example, I'm comparing the performance of accessing a single element in an array initially with device memory, where you have to use CUDA.add allow scalar to allow scalar indexing. And as you can see, that's pretty slow at 8.2 microseconds. Then in unified memory, it only takes 4.1 nanoseconds. So that's 3 orders of magnitude faster. And in comparison, indexing a native Julia CPU array takes around 2 nanoseconds. And I know that benchmarking at these nanosecond scales is a little iffy, but nonetheless, this shows that indexing GPU unified memory performs much, much, much better than indexing device memory does. And it's getting close to native CPU array indexing, which makes it possible to build hybrid CPU-GPU applications where you don't have to be afraid that indexing an array from the CPU side is going to kill your performance. So this makes it possible to propose a workflow where if you want to port a CPU application to the GPU, you of course start by switching over your CPU allocations to GPU allocations, which means changing array to CuArray inputs, but also changing manual allocations in your application to use generic APIs like similar or copy, which copy the array type that your input was using. But after that, if you want quick compatibility for your application, you just use unified memory. And all of the fallback CPU functionality, or just the functionality that you haven't ported yet, will just work out of the box. However, if beyond that, you want to make sure that your application is actually using the GPU in all places, you can still use device memory, which will trigger the scalar indexing and the pointer conversion errors I mentioned before, but it will very exactly point you to the places of your application that you still have to port. And porting there generally means switching from, for example, a for loop to a broadcast, or performing other kinds of array operations that have been implemented in CUDA.jl. It's also useful to mention here that because of Julia's multiple dispatch, it is possible to do this in a way that only applies to GPU code. So you might notice that a for loop performs better than a broadcast. Well, you can always keep your for loop implementation for the array type and only provide broadcast implementation for the CuArray version of your function. And finally, of course, you have to copy your device memory back to the CPU in order to inspect the results, whereas with unified memory, the memory is readily available on the CPU side. So this is the basic workflow if you want to port an entire CPU application to the GPU. But with unified memory, there is another alternative, which is relevant when you only want to port a very small part of your application, say some hotspots that you know can be easily parallelized or easily accelerated by a GPU. And for that, the new workflow is that you just keep your CPU array all over the place, and then you can simply wrap a CuArray around the original array object. You get a unified memory-backed CuArray out of that, which you can pass to CUDA.jl-based functionality, to a kernel function, to an array operation. For example, here I'm doing a broadcast assignment with the number 42. Afterwards, you synchronize the GPU, which means waiting for the results to complete. And then we can observe that our original array A has been updated by the GPU. Two things to note here. One is that this is currently an unsafe operation. That's also why it's called unsafe wrap. The fact that you as a user have to manage the lifetimes of A and B manually makes it unsafe. Specifically, as long as you're using the B array, which is derived from the CPU memory in A, you have to keep the A object alive as well. This is probably going to improve in the future, but for now, it is an unsafe API. Secondly, this uses HMM, which is Linux's heterogeneous memory management functionality whenever possible, making this fast. However, HMM is only available on recent GPUs and when using the open source NVIDIA driver. So you might want to make sure that your system is up to date and supports HMM before relying heavily on this functionality. It also needs to be said that unified memory has some trade-offs. There is a reason that we're not using this by default. For one, the on-demand paging, where the driver is now responsible for moving memory from the CPU to the GPU and back, incurs a certain amount of latency. On the other hand, it also may avoid memory copies in the first place. For example, if you have a kernel or an operation that is heavily sparse, by using on-demand paging, you only move those pages that your kernel accesses. Whereas with manual memory management, you would have to copy the entire array. It is also possible to overlap these copies that the driver does as part of its on-demand paging mechanism can be overlapped with computation, which is another benefit from using unified memory. However, on the flip side, one big disadvantage is that memory operations such as allocating an array and freeing an array are now synchronous, which means that if you call the free function, or if Julia calls the free function, then the system has to wait for the GPU to finish computing. And this is an important disadvantage, especially in a garbage collected language like Julia, because the garbage collector can kick in at any point. As a result, you can get free operations at any point during your applications, which in the case of unified memory would introduce synchronizations at various points in your applications. And this can be a disadvantage if your application is already having issues with fully saturating the GPU. But again, it has advantages as well. One of the more important ones is that it supports oversubscription. So you can actually allocate more memory than your GPU has available. Of course, this comes at a cost, because if you allocate or if you access memory while the GPU's memory pool is full, the driver is going to be migrating memory back to the CPU. So it supports oversubscription, but it isn't free. And this again is basically the bottom line here. Unified memory can have advantages for your application, but it may require you to optimize your application in certain ways. I expect this to improve in the future. So this is where we are at now. But for example, HMM in the Linux kernel is improving the usability of this framework. NVIDIA, with their latest hardware, such as the GH200, is adding hardware functionality to provide a much more high bandwidth and memory coherent unified memory interface between the CPU and the GPU. And other vendors, such as Apple, are moving towards a fully unified model as well. So in the future, I expect all these to improve, but for now, it is important to know that unified memory comes with certain trade-offs. But to summarize this part of my presentation of this webinar, CUDA.jl 5.4 greatly improves the usability of unified memory. It provides additional APIs, it greatly improves performance, and as such, unified memory becomes a viable tool to implement hybrid CPU-GPU applications. One approach is that you make your CuArray GPU allocations unified, and you can then simply pass them to CPU fallback code, because indexing into GPU memory from the CPU is now allowed. The alternative is you just keep on working with regular arrays and you wrap CuArrays around them, relying on the heterogeneous memory management subsystem in Linux. But as I just managed, there are trade-offs. So either after you've ported your application fully, you switch back to device memory, which is guaranteed to perform well, or you optimize your application in certain ways, specifically adding prefetch and other memory advice hints to your code will inform the driver how unified memory will be used and at which point in time it can safely prefetch the memory without it hurting performance. Finally, I'm going to briefly mention a couple of other highlights in CUDA.jl 5.4. I also want to mention that there has been a JuliaCon 2024 talk on the developments in CUDA.jl 5.4 over the course of the last year. So if you're interested in this, definitely check this out. But limiting myself to CUDA.jl 5.4 now, one of the more interesting changes that we now track the stream and device usage of CuArrays, allowing us to automatically synchronize or reconfigure your system when you're using CuArrays in one stream and then in another, or on one device and then on another device. For example, here, I'm allocating a task in which I allocate a CuArray. I'm fetching that array object, and then I'm using that object in my main task, which is a different task than the one I've allocated. So previously, this was unsafe because, again, all GPU applications execute asynchronously. So it was possible that this allocation wouldn't have been ready yet before we used it in a different unrelated task, which uses a different stream. CUDA.jl 5.4 now automatically detects that you're using this array on a different stream. And as you can see here in the profiler output, it automatically inserts a column to stream synchronize to make sure that all of the data that you've produced on one task is ready for use in another task. And we do something similar with multi-device functionality. In this tiny example, I'm allocating an array on device 0, and then I'm switching to device 1, which is a compatible device on which I'm executing a broadcast kernel. In this case, CUDA.jl detects that we're using this array on a different device, and it will configure the memory allocator to make sure that this memory is visible over NVLink or over another peer-to-peer mechanism to this different GPU. However, if I switch to another device that's incompatible, for example, device 2 here is incompatible with devices 0 and 1, we get an error when we try to use this memory. In this case, you would have to be responsible to still perform a copy that's staged through the CPU, which is as easy as just doing an explicit copy to bang. But we don't do this automatically because this incurs a very significant performance penalty. And as such, we want to be able that the user is aware that there is something happening behind the scenes, that you need to do something in order to ensure that this memory is visible. Another important improvement is that we now integrate much better with Julia's garbage collector. Before, we were only freeing up memory when the GPU device ran out of memory, which resulted in issues when people were, for example, still using a display manager, but it also resulted in costly garbage collector runs and costly memory management operations. In the latest version of CUDA.jl, we are now much more frequently collecting memory, specifically also when you allocate and also when you synchronize on the GPU, which is a point in time where you have to wait anyway for a device to finish. And this results in an improved memory usage, in cheaper garbage collection runs, and also in cheaper memory management operations. However, it is driven by a heuristic in which we look at the current memory pressure, in which we look at how much memory we freed the last time, in which we look at how much time we spent in the GC. So it is possible that your application is not perfectly covered by the heuristic at this point. So that's why we currently support running with and without this new feature, simply by toggling the Julia CUDA GC early environment variable. So if you have an application that suffers from high memory pressure or has had issues with the Julia garbage collector, and you don't see improvement by this functionality, it may be worthwhile to run with and without the functionality to see what is happening and to let us know how we could or maybe improve our heuristic to cover your application as well. And that's it for an overview of the CUDA.jl 5.4 features with a focus on how unified memory makes it much more easier to port applications from the CPU to the GPU. Now is probably a good time for some questions. So Sanjeev, back to you.
Yep. So thank you, Tim. You can type in your questions, and we can pick it up in the order we receive it. So yeah, please do let us know if you have any questions. There's one question from Richard Tim in the Q&A section.
Yes, so maybe I should repeat the question. The question is that this talk focuses on Linux and NVIDIA, but Apple also emphasized unified memory with ARM architectures. Are there similar developments for Macs? On the one hand, the situation is much easier on Macs because the memory is truly unified, meaning that there doesn't need to be any automatic memory management behind the scenes by the driver. However, we have not exposed that functionality to the user in a user-friendly way as we have done here. So CUDA.jl is the most mature backend that we have, which means that it's often the experimentation ground for new APIs. So at the point that we've figured out a good way to implement this where users are familiar with, these features will trickle down to other backends. And again, in the case of Metal.jl, which is the backend for our Apple GPU support, it will be much more straightforward to implement, with the exception of a couple of technical details, such as the fact that memory has to be page aligned, which is somewhat tricky. Nonetheless, again, as soon as we've gained some experience with unified memory API design in CUDA.jl, we will be adding these features in Metal.jl as well as other backends like OneAPI.jl and AMD GPU.jl.
Yeah, let's wait for a couple of more minutes in case there are any questions that might come in. So if you have any questions, do type it in the Q&A section and we'll answer them.
Yeah, a follow-up question. What the timeline for this would be? Honestly, no idea. Again, that one technical issue is actually holding us back to do this easy experimentation on the Metal.jl side as well. If you would be happy with using a array allocator that gives you page aligned memory, such as I think array allocators.jl, in that case, it would actually be straightforward to have this functionality in Metal.jl. So if this would be fine for your use case, definitely reach out and we could accelerate exposing this in Metal.jl. Again, the reason I haven't done so is because without the fact that you cannot simply take a Julia array as allocated on the CPU without it's aligning it first is going to be troublesome for most users anyway. So, which is why it hasn't been implemented yet.
Okay, seems like we have no other questions. So maybe we can call it a day.
Sure.
Thanks a lot, Tim, for the wonderful session. And thank you, everybody, for joining today's webinar. The recorded version will be uploaded on our website and you can watch it at your convenience. We will also email the record version to you shortly, and you can again obviously watch it at your convenience. And for future webinars, we'll upload there, or we'll put the calendar on our website, and you can certainly join us for upcoming and future webinars. Thank you, everybody, and have a great day.
Thanks. Bye.
Bye.